Good morning, students. In previous class, we have completed trends in the M+3 such that M+2 standard electrode potentials also. Even we started with the trends in stability of higher oxygen states. In that started with the halides we have seen. Okay, let us continue with our same thing now. Although vanadium oxidation number 5 is represented only by VF5, this is with respect to halides. The other halides, however, undergo hydrolysis to give oxohalides. Oxohalide general formula VOX3. Coming with vanadium, oxohalides general formula VOX3. Another feature of fluorides is their instability in the low oxidation states, example VX2. Generally, fluorides are stable in higher oxygen state when compared to lower oxygen state. Okay, X is equal to chlorine, bromine or iodine. Continuation. And the same applies to CuX. Same thing will be applied to CuX also. On the other hand, all Cu2 halides are known except the iodide. All copper halides are known, means with the oxidation number 2, but except iodide. In this case, Cu plus 2 oxidizes I minus to I2. That's why I minus is not stable in presence of Cu plus 2. Cu plus 2 oxidizes easily I minus to I2. That's why I minus is not stable in presence of Cu plus 2. Because of that, Cu plus 2 cannot combine with I minus. Is it okay? See, 2 Cu plus 2 plus 4 I minus gives rise to Cu2I2 plus I2. Cu2I2 is not formed. Cu2I2 only is formed. That's why Cu2I2 is not existed. However, many copper 1 compounds are unstable in aqueous solutions and undergo disproportionation. Meaning of disproportionation: same oxidation number will undergo oxidation and reduction. Now, they gave this example. See here. Left hand side copper oxidation number is +1. This one +2. This is 0. +1 oxidation number is becoming +2. Increase in oxidation number. Oxidation. +1 oxidation number is becoming 0. Decrease in oxidation number, which is called reduction. Same oxidation number is undergoing oxidation and reduction. This type of reactions are called disproportionation reactions. Same element will undergo oxidation and reduction. Here 2 Cu plus ions are there. One Cu plus ion will undergo oxidation and another Cu plus ion will undergo reduction. This is the example for disproportionation reaction. The stability of Cu plus 2 rather than Cu plus, this is very important point. Stability of Cu plus 2 rather than Cu plus is due to the much more negative delta H naught of Cu plus 2 than Cu plus, which more than compensates for the second ionization enthalpy of copper. Here actually we will think that Cu plus electronic configuration is argon 4s0 3d10. Cu plus 2 electronic configuration is argon 4s0 3d9. Completely filled electronic configuration must be more stable when compared to incompletely filled configuration. Like that we will feel, and we will think that Cu plus is more stable than Cu plus 2. But in aqueous solution, as copper contains high charge here +2, more number of water molecules will be surrounded by Cu plus 2 in water. When more number of water molecules are surrounded, more amount of energy will be released. That is called hydration energy. Here this Cu plus releases less amount of hydration energy. When more amount of hydration energy is released, Cu plus 2 is solvated easily and it will be stable in water, aqueous solution. So this point is very helpful. Definitely we can expect the question, why Cu plus 2 is more stable when compared to Cu plus, even though it has unstable configuration when compared to Cu plus. Because in aqueous solution, Cu plus 2 will be surrounded by more number of water molecules. Because of that, high amount of hydration energy will be released. Okay, that's why Cu plus 2 is more stable than Cu plus in aqueous solution. The stability of Cu plus 2 rather than Cu plus aqueous, in bracket they mention aqueous, is due to the much more negative hydration enthalpy of Cu plus 2. Much more negative means more amount of energy is released. That is the meaning. Okay, which more than compensated for the second ionization enthalpy of copper. Next, the ability of oxygen to stabilize the highest oxygen state. Now, till now we have seen the fluorides, halides. Now we are going to see about oxides. Oxidation states of D block elements with respect to oxides. The ability of oxygen to stabilize the highest oxygen state is demonstrated in the oxides. Actually, ability of oxygen to stabilize the highest oxygen state is demonstrated in the oxides. The highest oxidation number in the oxides coincides with the group number. This point already we know from 11th class redox reactions chapter. Oxidation number of the element should not cross its group number. Maximum oxidation number of the element should not cross its group number and is attained in Sc2O3 to Mn2O7. Manganese group number is 7. So in Mn2O7, manganese oxidation number is 7. Scandium group number is 3. So in Sc2O3, scandium will get plus 3 oxidation number. Okay. Beyond group 7, no higher oxides of iron above Fe2O3. So above group 7, group 8, like that, there is no chance of showing higher oxides. Only iron above, no higher oxides of iron above Fe2O3. Above Fe2O3 means FeO6, FeO8, like that it won't be shown. FeO4, like that it is not possible or known. Although ferrates, FeO4 minus 2, ferrates, FeO2 minus 2 are formed in alkaline media. Alkaline means basic media, but they readily decomposes to Fe2O3 and O2. These are also not stable. FeO4 minus 2 are also not stable. Immediately they will be decomposed to Fe2O3 and O2. Besides the oxides, oxocations stabilize V5 as VO2 plus, V4 as VO plus 2 and titanium 4 as TiO plus 2. You know how to calculate the oxidation numbers, man. For one thing I am going to explain, VO2 plus. Let it be oxidation number of vanadium is X plus 2 into minus 2. General oxidation number is minus 2 for oxygen. How many atoms are there? 2. X plus 2 into minus 2 is equal to plus 1. X minus 4 is equal to plus 1. X is equal to 4 plus 1 is equal to 5. So vanadium oxidation number in VO2 plus is 5. That's why they wrote V5. V5 as VO2 plus, V4 as VO plus 2 and titanium 4 as TiO plus 2. The ability of oxygen to stabilize these high oxidation states exceeds that of fluorine. When compared to fluorine, oxygen has high capability to stabilize these higher oxidation states. Okay, thus the highest manganese fluoride is MnO4, whereas the highest oxide is Mn2O7. Manganese fluoride is MnO4, whereas the highest oxide is Mn2O7. The ability of oxygen to form multiple bonds to metals explains its superiority. In the covalent oxide Mn2O7, each manganese is tetrahedrally surrounded by oxygens including MnO-Mn bridge. Mn2O7 structure. This manganese 1, 2, 3, 4 tetrahedral structure. This manganese also 1, 2, 3, 4 tetrahedral structure, in which two tetrahedrals are joined by like one oxygen. This is the structure of Mn2O7. With MnO-Mn bridge. The tetrahedral MO4N- ions are known for vanadium 5, chromium 6, manganese 5, manganese 6 and manganese 7 ions. This is not Mn, M. M is metal, where M is nothing but vanadium, chromium, manganese, okay, manganese 5, manganese 6 and manganese 7. Like that general representation of oxide they have shown here. Is it okay? Now table 8.6 depicts the oxides of 3D metals. Scandium, only one oxide, Se2O3, oxidation number +3. Titanium can show 3 oxides, vanadium 4, chromium 4, manganese large number 1, 2, 3, 4, 5. Up to here, ability of formation of oxides increased. From again decreased. Iron can show 3. This star mark represents mixed oxides. Fe3O4 is the mixed oxide of Fe2O3.FeO. Jointly Fe3O4. It is called mixed oxide. That only they mentioned star mark. Fe2O3, FeO represented as Fe3O4. Okay? Fe3O4. CO3O4 also mixed oxide. NiO, CuO, Cu2O, ZnO. These are the oxides which are shown by first row transition elements. Okay, easily we can calculate the oxidation numbers. In Mn2O7, oxidation number of manganese is 7. In ZnO, oxidation number of zinc is +2. In NiO, oxidation number of nickel is +2. Easily with respect to oxygen, general oxidation number of oxygen is -2. General oxidation number of oxygen is -2. By using that, any oxidation number of metal can be found. Okay, this is about the completion. Sorry, one more thing is there. Standard reaction potentials, chemical reactivity and E0 values. By this, we are going to complete the reduction potential values. Okay, transition metals vary widely in their chemical reactivity. Many of them are sufficiently electropositive to dissolve in mineral acids. Maximum of them are high reactive than hydrogen and they can be dissolved in acids easily. They are highly electropositive enough to dissolve in mineral acids, although a few are noble. For noble metals, example, platinum, gold, silver, these are all examples for noble metals. That is, they are unaffected by single acids. That's why gold is affected by aquaresia. Concentrated HCl, concentrated HNO3. Aquaresia. So, single acids cannot affect these noble metals. They are unaffected by single acids. The metals of the first series, with the exception of copper, are relatively more reactive. Except copper, metals high reactive is nothing but they want to lose the electrons easily and are oxidized by 1 molar H plus ion. Oxidation means they will lose the electron. Observe every point carefully. The metals of the first series, with the exception of copper, generally copper will undergo reduction instead of oxidation. are relatively more reactive and are oxidized by 1 molar H+, though the actual rate at which these metals react with oxidizing agents like hydrogen ion is sometimes slow. Sometimes it will be slow also. For example, titanium and vanadium in practice are passive to dilute non-oxidizing agents at room temperature. Passive means they won't react. Passive means less reactive. To dilute non-oxidizing agents at room temperature. The E0 values for M+2 such that M indicate a decreasing tendency to form divalent cations across the series. Here we have seen the tabular column also. By seeing the tabular column easily we can understand what about the E0 values for M+2 such that M. This general trend towards less negative E0 values is related to the increase in some of the first and second ionization enthalpy values. First and second ionization enthalpy values are getting increased because of that. Already I told, when we require high amount of ionization enthalpy, the process will not be taken place. Oxidation process will not be taken place easily. They want to reduce. This general trend towards less negative E0 values is less negative. Less negative means they want to undergo reduction. High negative means they want to undergo oxidation. Is it okay? Is related to the increase in the sum of the first and second. If the first and second ionization enthalpies are increased, more amount of energy is required. If more amount of energy is required, automatically that process oxidation will not be taken place easily. Preferably they will undergo reduction. Okay, that one clearly we have seen with the help of that tabular column. This general trend towards less negative E0 values is related to the increase in the sum of the first and second ionization enthalpies. It is interesting to note that the E0 values for manganese, nickel and zinc are more negative. More negative is nothing but they want to prefer to undergo oxidation. More negative than expected from the general trend. That one we have seen expected value and calculated value. This diagram. More negative than expected from the general trend, whereas the stabilities of half-filled D subshell, D5 in Mn+2 and completely filled D subshell in zinc are related to their E0 values. For nickel, E0 value is related to the highest negative enthalpy of hydration. For nickel, it will be considered with highest enthalpy of hydration. Okay, an examination of the E0 values for the redox couple M+3 such that M+2 shows that Mn+3 and CO+3 ions are the strongest oxidizing agents. Easily they will undergo reduction to make others to undergo oxidation in aqueous solutions. The ions Ti+2, V+2 and Cr+2 are strong reducing agents and will liberate hydrogen from a dilute acid easily. 2Cr+2 plus 2H plus gives rise to 2Cr+3 plus H2. Cr+2 is converted to Cr+3, increase in oxidation number, which is called oxidation. Okay, H plus will undergo reduction to form H2. That is about chemical reactivity and E0 values. By this, trends in M+2 such that M, whatever it is, related to standard reduction potential values, it was completed for us. Okay, after that, we need to go through magnetic properties. Coming to magnetic properties, to explain the magnetic properties of D block elements, we need to classify the elements into three categories depending on magnetic properties. So, depending on magnetic properties, D block elements are classified into three types: diamagnetic substances, paramagnetic substances, ferromagnetic substances. The substance which has no unpaired electrons are coming under diamagnetic substances. Diamagnetic substance has no unpaired electron. They are weakly repelled by the magnet. Diamagnetic substances have no unpaired electrons. They are weakly repelled by the magnet. Paramagnetic substances, the substance which has one or two unpaired electrons is called paramagnetic substance. Paramagnetic substances are weakly attracted by the magnet. Ferromagnetic substance which has greater than 2 unpaired electrons is called ferromagnetic substance. These ferromagnetic substances are strongly attracted by the magnet. If you remember, in solid state term 1, we have discussed this type of things: diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, ferrimagnetism also we discussed. But that 5 types no need here. Hardly we will go through these 3 types only. Those are diamagnetic, paramagnetic and ferromagnetic. Okay, ma? So, diamagnetic substances are weakly repelled by the magnet, which has no unpaired electron. After writing the configuration, we can check with how many unpaired electrons are there. If that substance has no unpaired electron, then that is coming under diamagnetic substance. If it has 1 or 2 unpaired electrons, then that substance comes under 1 or 2 unpaired electrons, then that substance comes under paramagnetic substance. If that substance has more than 2 unpaired electrons, then it comes under ferromagnetic substance. Example, Fe+2. Fe+2 electronic configuration is argon 4s0 3d6. 4s0 contains no electrons, 3d6. 1, 2, 3, 4, 5, 6. How many unpaired electrons are there? 4 unpaired electrons are there. Fe+2 has 4 unpaired electrons, which is greater than 2. So it comes under ferromagnetic. Strongly attracted by the magnet. Even iron. iron electronic configuration is argon 4s2 3d6. Even iron also has 4 unpaired electrons. It comes under ferromagnetic substance only. Okay, that's why iron, if you keep nearby magnet, it will be strongly attracted by the magnet. Okay, now magnetic field will be measured in terms of units Bohr magneton. Magnetic field units will be measured in terms of units Bohr magneton. By using magnetic susceptibility experiment, magnetic moment of any substance can be measured. By using magnetic susceptibility experiment, magnetic moment of any substance can be measured. Okay, after finding the magnetic moment value, magnetic moment is represented by mu. Okay, after finding the magnetic moment value, magnetic moment is equal to root of n into n plus 2, where n is equal to number of unpaired electrons. We can find the number of unpaired electrons present in that metal or any ionic form by using mu values. Mu values are calculated from magnetic susceptibility experiment. Are you okay, ma? By using magnetic susceptibility experiment, magnetic moment of any substance can be measured. Okay, then mu value is known to us. Then we have a formula, mu is equal to root of n into n plus 2, where n is equal to number of unpaired electrons. Remember this formula, it is highly useful not only here, in coordination compounds also it is very useful. Even in coordination compounds also we might have gotten this formula. Remember carefully. Now we will see the theory part now. When a magnetic field is applied to substances, mainly two types of magnetic behavior are observed, diamagnetism and paramagnetism. Diamagnetic substances are repelled by the applied field, while the paramagnetic substances are attracted. Substances which are attracted very strongly are said to be ferromagnetic also. In fact, ferromagnetism is an extreme form of paramagnetism. That only. Two unpaired electrons are there means weakly attracted by the magnet, which is paramagnetism. Extreme of that one, greater than two unpaired electrons, which is strongly attracted by the magnet. In fact, ferromagnetism is an extreme form of paramagnetism. Many of the transition metal ions are paramagnetic in nature because they contain less than two unpaired electrons or equal to two unpaired electrons. Paramagnetism arises from the presence of unpaired electrons, each such electron having a magnetic moment associated with its spin, angular momentum and orbital angular momentum. For the compounds of the first series of transition metals, the contribution of the orbital angular momentum is effectively quenched and hence is of no significance. Actually, in atomic structure, we have discussed with this type of quantum numbers: spin angular momentum and orbital angular momentum. But we will concentrate on only spin angular momentum, that is plus half and minus half signs. See, for the compounds of the first series of transition metal, the contribution of the orbital angular momentum is effectively quenched and hence is of no significance. So orbital quantum number significance is not there in transition series. So we are depending on only spin angular momentum, plus half, like that. For these, the magnetic moment is determined by the number of unpaired electrons and is calculated by using the spin-only formula. This is called spin-only formula, that is mu is equal to root of n into n plus 2, where n is called number of unpaired electrons and mu is the magnetic moment in units of Bohr magneton. A single unpaired electron has a magnetic moment of 1.73 Bohr magnetons. A single unpaired electron has a magnetic moment of 1.73 Bohr magneton. The magnetic moment increases with the increasing number of unpaired electrons. This is known thing to us. Thus, the observed magnetic moment gives a useful indication about the number of unpaired electrons present in the atom. In the form of a tabular column, we have got in this one. The experimental data are mainly for hydrated ions in solution or in the solid state. Okay, see. Scandium plus 3, Se plus 3, configuration 3d0. No unpaired electrons are there. 0. Magnetic moment calculated 0. Observed also 0 only. This is calculated means depending on number of unpaired electrons formula. Spin only formula. This is experimental value. Next, titanium plus 2. 2 unpaired electrons are there. Sorry, titanium plus 3, 3d1, 1 unpaired electron is there. Magnetic moment 1.73, observed 1.75. Next, 2 unpaired electrons are there, 2.84, 2.76. Like that, calculated values and observed values are given. Here the thing is, no need to remember these values. See, Zn plus 2, 3d10, 0 unpaired electrons are there. Because every electron is paired. Then 0 unpaired electrons are there. Calculated value 0, observed value is also 0 only. Okay, just to remember this one. But this is very easy for us to understand. If you are able to write the electronic configuration, easily we can say the magnetic moment value, number of unpaired electrons value, and depending on number of unpaired electrons, we can calculate the magnetic moment easily by using the formula mu is equal to root of n into n plus 2. That is very important formula, ma. Remember that carefully. Spin only formula, where n is equal to number of unpaired electrons. Okay. Maximum, if you have 5 unpaired electrons, mu value 5.92. It should not cross 6. It will not touch the 6 also, because mu is equal to 5 into 7, root 35. Root 35, definitely 35 means less than 36. Root 36, 6. So that value is less than 6. That's why 5.92. If you see 5.92 mu value, number of unpaired electrons 5. If you see 4.82 like that, number of unpaired electrons equal to 4. 3 point something, number of unpaired electrons equal to 3. No need to think any other thing. Okay, ma? This is about magnetic properties. Our next concept is formation of colored ions. These are all going to be completed very fastly. Main points, ionization enthalpies and oxidation states only, they took time. But now these are all simple things only, ma. Easily we will complete. And these are all easy things also, easy to remember also. Formation of colored ions. Simple. Any metal ion or metal which contains unpaired electrons will be colored in nature, definitely. If it has unpaired electrons, definitely it will be colored. If it has no unpaired electrons, it is colorless. This colored nature we have explained in D block elements also. Crystal field theory successfully explained that one. What is that? Crystal field theory. Because of transitions of DD transitions of electrons, these colors will be obtained. Like that we have seen. Okay, ma? Already we have seen that. We have seen that in D block elements, ma. If a central metal ion has unpaired electrons, then it will show some color, definitely. If it has no unpaired electrons, it will not be color. It will not be colored in nature. The thing is here, in the exams we cannot expect any sort of particular color. Suppose Fe plus 2 is in which color, Cu plus 2 is in which color, like that they won't ask. Is it okay? But whether it is colorless or colored, they will ask. Then at that time what we will say? By checking the central metal atom electronic configuration, if it has unpaired electrons, then it must be colored. Like that we have to come to one conclusion. Now let us see the explanation here. Formation of colored ions. When an electron from a lower energy d orbital is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed. Unit 9 we have seen clearly in crystal field theory. Please once again refer that one. In coordination compounds crystal field theory, we have seen that explanation. The color absorbed corresponds to the complementary color of the light absorbed. The frequency of the light absorbed is determined by the nature of the ligand. So cyanide, hydrogen, water, NO2, like the different ligands we have. So that ligands will decide the color of the complex. Is determined by the nature of the ligand. In aqueous solutions, where water molecules are the ligands, the colors of the ions observed are listed in table 8.8, where water is ligand. A few colored solutions of D block elements are illustrated in figure 8.5. So they were explained in figure 8.5. Colors of some of the first row transition metal ions in aqueous solutions from left to right. Vanadium plus 4, this is the color. Vanadium plus 3, this is the color. Manganese plus 2, Fe plus 3, CO plus 2, Ni plus 2 and Cu plus 2. Dark blue color Cu plus 2. Aquated. See, table 8.8 shows that colors of some of the first row transition metal ions. Aquated is nothing but water is the ligand here. Sc plus 3 has no unpaired electron because its configuration is 3d0. When it has no unpaired electron, it is colorless. Ti plus 4, 0 unpaired electrons, so colorless. Ti plus 3, 3d1, 1 unpaired electron is there, it is purple. Depending on 1 unpaired electron, it is not purple ma. Depending on the ligands, it will be. Here, every metal ion has same ligand, water only. Is it okay? Depending on that, they gave the colors also. V plus 4, 3d1, 3d2. See, whatever the color if you see, definitely they have unpaired electrons. 3d4, 3d5, 5 unpaired electrons are there. 3d5, 5 unpaired electrons. 3d6, 4 unpaired electrons. 3d6, 3d7, 4, 3 unpaired electrons. 3d8, 2 unpaired electrons. 3d9, 1 unpaired electron. Everything has unpaired electron. Then it must be colored in nature. Coming to Zn plus 2. 3d10, it is colorless because it has no unpaired electron. I hope you are clear about this colors also. So final conclusion of this one, the central metal ion, if it has unpaired electrons, then it must be colored in nature. If it has no unpaired electron, it is not a color. Here colorless is nothing but white color ma. In chemistry, colorless is nothing but white color. Okay? Next. Formation of complex compounds. This one also we have discussed in coordination compounds separately. See, here heading is small thing only. Formation of complex compounds, heading is small thing only. Regarding this one separate chapter is there. That is 9th chapter for us. Complex compounds are those in which the metal ions bind a number of anions or neutral molecules giving complex species with characteristic properties. A few examples are FeCN6 3-, FeCN6 4-, CuNH3 4 2+, and PtCl4 2-. The chemistry of complex compounds is dealt with in detail in Unit 9. The transition metals form a large number of complex compounds. This is due to the comparatively smaller size of the metal ions, their high ionic charges, and the availability of d orbitals. These reasons are very important. Remember these reasons, ma. This is due to the comparatively smaller sizes of the metal ions. Left to right, what will be happen to size decreases. So smaller sizes of the metal ions, their high ionic charges, and the availability of d orbitals for bond formation. Okay, because of these reasons, they are able to form complex compounds. Next, catalytic properties. Out of total periodic table, D block elements are acting like good catalysts. D block elements are acting like good catalysts. Why these D block elements are acting like a good catalyst? Even F block elements also. Okay, why these D block elements are acting like good catalysts? What are the characteristics keep them to be acted like a good catalyst? Now we are going to see. The transition metals and their compounds are known for their, even not only metals, their compounds also. Example V2O5 is a catalyst in preparation of H2SO4 contact process, sulfuric acid preparation. V2O5 is the catalyst, like that. Okay, Fe2O3 is also catalyst, Fe is also catalyst. Transition metals and their compounds are known for their catalytic activity. This activity is ascribed, it is elevated to their ability to adopt multiple oxidation states. Mainly, they are able to show different oxidation states, which is nothing but variable oxidation states, and to form complexes. That is the main characteristic which keeps them to be acting like a good catalyst. Vanadium 5 oxide, that only V2O5 ma. Example I told na, vanadium 5 oxide in contact process, preparation of sulfuric acid. Finely divided iron, I told example iron also in Haber's process, preparation of ammonia, and nickel in catalytic hydrogenation, preparation of hydrocarbons are some of the examples. Catalysts at a solid surface involve the formation of bonds between reactant molecules and the atoms of the surface of the catalyst. First row transition metals utilize 3d and 4s electrons for bonding. This has the effect of increasing the concentration of the reactants at the catalyst. This one mechanism we have seen in surface chemistry. Same thing we are discussing here at the catalyst surface, and also weakening of the bonds in the reacting molecules. The activation energy is lowered by the catalysts by their surface energy. Activation energy of the reaction is lowered by the catalyst by the surface energy of the catalyst. Because of that, the reaction is getting faster. Also because the transition metal ions can change their oxidation states, they become more effective as catalysts. For example, iron 3 catalyzes the reaction between iodide and persulfate ions. 2I minus plus S2O8 minus 2 gives rise to I2 plus 2SO4 minus 2. This is catalyzed by Fe plus 3. An explanation of this catalytic action can be given as: first 2Fe plus 3 reacts with 2I minus to form 2Fe plus 2 plus I2. See, ability of iron to convert from plus 3 to plus 2 is helping here to be acting like a catalyst. That's why, due to the comparatively smaller size of the metal ions, their high ionic charges and thus availability of d orbitals, even ascribed to their ability to adopt multiple oxidation states. This is explained here. Fe plus 3 is able to be converted to Fe plus 2. Again, Fe plus 2 reacts with second reactant S2O8 minus 2 to be converted to Fe plus 3 plus 2SO4 minus 2. Our products are I2 and SO4 minus 2. We got them along with Fe plus 3 came back. Fe plus 3 is involved in the reaction. Again it came back. Meaning catalyst does not involve in the reaction. Like that we can say one statement. Is it okay, ma? This is the example. An explanation of this catalytic action can be given as. So here the important thing is why these are acting like a catalyst, good catalyst. Why these are acting like a good catalyst? That main point is they have their ability to adopt multiple oxidation states and to form complexes also. Why they are able to form complexes? This is due to the comparatively smaller sizes of the metal ions, their high ionic charges, and the availability of d orbitals for bond formation. These are the explanations, these are the reasons you need to keep it in mind and memorize when we are going to get this type of questions. Is it okay, ma? This is about catalytic properties. By this, up to catalytic properties we have completed. In the next class, we will go through formation of interstitial compounds and Li formation. And almost we came to the last one. If we have completed with formation of interstitial compounds and Li formation, we are going to complete the D block elements. Because 8.4 fully it was deleted. 8.4 fully it is deleted. So we are going to complete the D block elements. After the D block elements, directly we will go through inner transition elements F block. In that, what are the topics we have? In the next class, I will discuss that one and I will go through that class. By one more class, we are going to complete this chapter. Is it okay, ma? By one more class, we are going to complete this chapter. In today's class, what are the things we have discussed? Chemical reactivity and E0 values, magnetic properties, formation of colored ions, formation of complex compounds, and catalytic properties. Reasons, everything we have seen, and this is about today's class. I hope everyone you understand the concept well. According to that, you have to practice, and by one more class we are going to wind up this chapter. Okay, if you have any sort of doubts, you can contact me through WhatsApp or through call also, no problem. I will clarify your doubts. I am ready to explain anytime, no problem. Thank you all. Have a nice day.